Okay, so I'm going to speak about effective rational approximation of spheres. So let me first maybe recall briefly the context of this problem, Diophantine approximation. So we want to approximate a real vector alpha by rational vectors PQ. Alpha is in RD. PQ are in PD times N. So, and we measure the quality of this approximation against some function of the complexity Q. And let me take this decreasing function of the denominator with this exponent. So 1 plus 1 over d, this is the critical exponent. So in the Khinchin dichotomy, this is the largest exponent that gives, for which almost every vector is well approximable. So we have that every constant we have, and for almost every alpha in RD, we have infinitely many such pairs that satisfy this inequality. So a natural refinement of this question is to count these solutions up to some denominator. This is another. So I call star the first inequality, and if I take this system of inequalities, I call it this other kind of stars. And so we can define some counting function of these pairs for given C for a height t. The number we define the counting function of pairs such that we have star. Oh yes, sorry. Okay, so this is the counting function of the pairs that satisfy the system of inequalities, and this counting function is already well estimated. So we have a result from Schmidt in 60. We have an effective estimate of LTC. LTC of alpha is, so this is some constant times the height t plus square root of t and then some log 3/2 plus epsilon for almost every alpha. And yes, another refinement of this question, and this is more specifically the topic of my talk, is to restrict this approximation to a subset of RD. For example, some level set of a quadratic form. And here and then this is called, that's what we call intrinsic Diophantine approximation. And I look more specifically to the sphere. So I approximate real vectors on the sphere by rational vectors on the sphere. Here I require that P over Q is also on the sphere, and here I cannot have this quality of the approximation. The critical exponent for this intrinsic Diophantine approximation is 1. So this was a result by Klainbock and Merrill in 13, I think. They showed that the critical exponent is 1, independent of the dimension of the sphere. So for this inequality, we have, again, almost every vector in SL is well approximable. So we have infinity of such pairs. And we can count again the solutions up to some height. And here, for convenience, Yes. Yes, just a slight modification. It gives more convenient for the computations. So again, yes, we have this counting function. Here we require, moreover, that PQ is in Sn. And for this intrinsic counting function, we have Alam-Ghosh gave an effect, quantitative estimate 2 years ago. So they showed that the number of pairs that satisfy the system. This counting function is asymptotic to T times some computable constant Cn when T goes to infinity for almost every alpha on the sphere. Yes. Exactly, yes. No, the error term, it's the result I would like to present. Maybe I should write a little bit lower, otherwise we have reflection. Yes, so the result I want to present is the estimate of the error term. We have the same counting function. So this is constant depending only on the Diophantine constant C here and the dimension n of the sphere. And the error term is we have a power saving. We have a power saving delta such that for almost every alpha on the sphere, we have this estimate. So it's not what the square root power saving one could hope or expect as in the classical approximation, but yes, it's still so we know that the error term is smaller than the main terms. Okay, and I mean, at least for me, it was really a pleasure to put hands on this on the beauty of Dani correspondence and all this approach, dynamical system approach to this number theoretic problem. So I hope. Yes. Yes. For every C, it has infinitely many solutions. Yes. This is for almost every alpha on the sphere. So we are here in the Kinshin dichotomy. Yes, I think it's yes. It's the inequality I want to consider, for which we have infinitely many pairs. Am I right? Yes. Yes, depend on n. Depend only on n. The dimension. Result is for RD and this was here, but you have the same. Sorry. C times T plus an alpha? No, maybe it's not the same. So not the same constant. Not the same constant. Same main term. Same main term. Yes. Is it surprising or? Well, I mean. Oh yes, exactly. I mean, almost, because it's. I mean, it's the main term in the way that it is proportional to the height t. Yes. Yes. So we go on. I mean, the counting function. Now I will study later is the one for this that which correspond to this system of inequalities. Okay. Yes. So maybe I will tell. So I first wanted to recall briefly this approach from Diophantine approximation to homogeneous dynamics. Yes, and it's very natural. I found it very natural to this approach to approach this Diophantine approximation problem with homogeneous dynamic, and this approach was already explicitly described by Klainbock and Merrill in 13, and then developed by Alam-Ghosh 2 years ago. It starts with the following. So we first embed the sphere in the light cone of the zero set of quadratic form in RD, Rn+2. So quadratic form of inertia n1, or here n+1, 1. Maybe I can make a picture at this point. This is the light cone. D, so I embed in of the sphere. This is the last coordinate. Maybe coming out of the blackboard, the coordinate xn+1. So the embedding is simply for real vector alpha on the sphere, I associate alpha 1. So this would be alpha 1, the embedded sphere. And then the very transparent geometry of the problem is to say that a rational vector PQ on the sphere is close to alpha. This means that alpha. So here I have E over Q1 is close to alpha. Exactly when the integer point PQ on the light cone is close to the array to the ray through alpha 1. PQ on integer points on the light cone is close to the ray through alpha 1. Okay, so we transformed the approximation problem with the dense set into approximation problem with a discrete set, integer points on the light cone, for which we can have convenient dynamical. So maybe here I introduce some notations to formulate the problem into dynamical language. So I will denote lambda naught the set of integer points on the light cone. This will play the role of the standard lattice on the light cone. Then I denote G. This is the group of linear transformations that preserve orientation preserving linear transformation that preserves the quadratic form Q. I take connected component of it. So this is isomorph to SON. This is isomorph to SON plus 1, 1. Yes, then I consider I denote gamma. So this is the stabilizer in G of this standard lattice lambda naught. So this is a lattice in G. And I will I will say that lambda is a lattice in the light cone. If lambda is the form G times lambda naught. So the space of lattices in the light cone is the set of G lambda naught for G in G, big in capital G. This is isomorph to G mod gamma, and this is the homogeneous space for this the homogeneous space I want to study. Yes, and maybe also interesting, and I will also denote K. So this is the subgroup of subgroup in G which preserve the last coordinate. This is SON plus 1, 1. So this is SN plus 1. And also a particular subgroup which will be useful is this group one parameter subgroup here in the first diagonal En, and then cosinus hyperbolic T minus sinus hyperbolic T minus sinus hyperbolic T cosinus hyperbolic T. This is if I change the coordinate system, I mean, in this convenient coordinate system where the quadratic form has this convenient form, if I change the coordinate system, I have a diagonal, the classical diagonal subgroup E minus ET, E minus T. Yeah, so with these new notations, I can reformulate this observation. This is a geometric observation. So now PQ is the pair PQ is a solution so satisfies my system of inequalities exactly if and only if the rotation of this pair PQ by a particular specific rotation K lies in some domain ETC on the light cone. I will specify here for some specific K. This is the idea Uri also introduced earlier this week. The result we are looking for is for almost every alpha. We transform this randomness on alpha by a randomness on K on the orbits on the lattices K lambda naught. So I rotate PQ by the rotation K, and K is such that K alpha 1, K brings alpha 1 to the 0, 0, 0, 0, 1, 1 vector on the lattice. So the rotation that brings K is this particular. So for every K such that K is in K such that. So the rotation K which bring alpha 1 to this point, 0, 0, 0, 1, 1, should bring PQ close to this ray, and this is the domain ETC. It's a very thin domain along this array. So this is ETC. Is this geometric? Yes. It's not complicated. ETC. So it's the set of real vectors. I think that's 2x plus 2xn plus 2. I mean, for me at least, I don't see the intuition. I mean, the visual. I don't visualize this formula on this n-dimensional light cone, but n plus 2, n plus it's y. So this should be smaller than C2. This is the first constraint in this for this domain, and then the difference is smaller than ET. I think this is the. I think maybe Anish remembers better. I think this is the formula. Yes, around this and yes, this domain is interesting because this subgroup really will contract this direction of interest, this area of interest in the light cone. So yes, so now that I formulated this problem like this, I can write explicitly what the counting function is. So this is simply the number of integer points in this domain ETC, which are also coming from the rotation of this standard lattice under K. K is will be always this K that does exactly this rotation of alpha 1. And the first thing is that this ETC is not exactly, so this is the real domain where my solutions lie. This is the real domain I want to count. But I need to approximate it by another domain, which will offer the nice tessellation under A. This is, I will call this approximating set FTC. And this approximation is what Alam-Ghosh, yes, this is the sandwiching. So they sandwich ETC between, ETC between FTC plus some constant sets. For constant R0. And here we have some parameters. So we have a parameter here for this the left side of this sandwiching. So I need to subtract some constant, some constant sets, some finite sets that contain finitely many integer points. And so the only difference between, I mean, the difference from this sandwiching suggested by Alam-Ghosh is that we need here to make it effective, because we don't want it to spoil the error term in the final estimate. This needs to be effective. So this parameter L here needs to be, so it's a parameter that depends on T, and we'll make it effective and control. One needs to control this sandwiching. And this set is more convenient because it is a tessellation under AT. Oh, now, if you allow me, I will take T now as an integer. I will denote it N. So it's a tessellation of some tessellation by under the subgroup A, and here F1C is some elementary domain. This is again the idea you talked about earlier this week. We bring everything to height 1. No. So we need to change a little bit this defining equations. So this is modulo, well, n is t is an integer, let's say. Okay, so and now this is, it will be very soon now a very common, it will look like something very common to you. So if, sorry? Oh, yes, thank you. Thank you. So now if I take I introduce the Siegel transform of a function, continuous function compactly supported on the light cone. So this is f hat of the lattice lambda on the light cone. This is the sum of f at over all points in the lattice. So when if I take the characteristic function of this set, this is exactly the sum. The counting points in this intersection is exactly the sum over t to n minus 1 of the characteristic function Siegel transform of this set. Let's write it like this: at k lambda naught. Okay, so what this says is that studying this counting function is actually studying these ergodic averages, the ergodic averages of this Siegel transform. Should I write maybe larger? So we study these ergodic averages. Ergodic averages of this, I will denote it chi hat. This is the characteristic function of this elementary set I'm interested in. So I will study these ergodic averages on this subspace. I will denote it y. This is k times lambda naught. This is a subspace of the space of lattices on the light cone. This is also what Alam-Ghosh did, and they used that the action of A on X is ergodic. So these ergodic averages, so in the work of Alam-Ghosh, simply they use that this ergodic averages converge pointwise almost everywhere to the average on X of the Siegel transform. This is Birkhoff, pointwise Birkhoff ergodic theorem for almost every y. Let's write it. Yes, for almost every y in X. And then they show that it is also true for almost every y in Y. And the average of the Siegel transform is simply, it's also the average on the light cone of this characteristic function. This is a Siegel mean value theorem. So this is the volume of the set, the volume of F1C. So this is exactly the theorem of Alam-Ghosh above. So the number of approximants is proportional to this volume times t. So yes, and our result, if we want to make this estimate effective, we need effective equidistribution, effective pointwise equidistribution almost everywhere. So that's maybe the point where I'll talk about effective equidistribution. So let me maybe first Yes. You mean they are not? Yes, it's K is not unique. You're right. K is not unique, but yes, maybe this notation may be here a little bit not 100% exact. But what is important is that full measure sets on the sphere correspond to full measure sets on K. So I want a result which is for almost every alpha. So I will find some estimate of this quantity for almost every K. Why? Because I think your question is this: how do you choose K? Because K is not unique. That's at this point is not important. I want some result for. Again, I transform the randomness on alpha to a randomness over K. So
you just pick any K.
Any K.
And then you use the usual stable, unstable direction.
Exactly.
K.
Yes, exactly. Yes. Exactly.
So your initial alpha.
Yes. 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 Or even yes, more radically, you can forget about this for a while. We are going to study this number of points, and we will have a result which is for almost every K. And actually, this corresponds to almost every alpha. Thank you. Yes, this is a good question because it allows me to reformulate the theorem in terms of ergodic averages. So what we want, what we actually claim, is that these ergodic averages or y. So this is the average of this character of the Siegel transform of the characteristic function on X, sorry, plus some error term of n. This is just a reformulation of the theorem. So I claim that these ergodic averages equidistribute to the average of the Siegel transform on the homogeneous space plus some error term, which is n to some negative power, for almost every alpha. And yes, and the idea to have such almost everywhere pointwise equidistribution is to use L2 bound, an L2 bound on these ergodic averages and derive almost everywhere bound on these ergodic averages. The idea is to have L2 bound on these ergodic averages will give me, I hope I'm not beyond the, maybe I'm already beyond the, so this will give me almost everywhere bound for these ergodic averages. And this go on here. This is a yes, I quote Theorem Klainbock, Barak, Weiss, and Shah. Kleinbock. I think this was in 15 or 13. 13, I think. Let's say 13. I don't remember yet. I can check quickly. 15. I think the idea, as you mentioned it in the result, the idea dates back to Schmidt, and the claim is the following. So yes, it's more general. So I have any y mu probability space. And some measurable function on y cross n in R. So if I have the following L2 bound on the ergodic averages of F, so if I have that the L2 bound of ergodic averages of F, or for any range AB, if the L2 bound of these ergodic averages is bounded, and the bound should be of this quality, of this preciseness, for every integers AB, then I have an almost everywhere bound on the ergodic averages. This is yes. For almost every y. So yes, if I manage to have an L2 bound of this quality on my ergodic averages, then I will be able to have even a square root power saving. But indeed, this is something I will not be able to have for my Siegel transform. But at least this is the first remark: is we can make it, if we don't have this bound for L2, we can make it a little bit. If we have this bound only for P smaller than 2, we still can have some power saving here, some estimate. This will look like as 1 minus 1 minus over P. Yes, this is 1 plus 1 over P, so it's less. We have less better power saving, but at least we do with what we have. The remark works also with LP instead of L2. Sorry? I think I think in your result you say that the idea was already present in actually an important ingredient or tool technique in this proof is to use the Schmidt decomposition. When you decompose this the interval 0 to n in dyadic small intervals, and you use Borel-Cantelli lemma to have this estimate. I think now it became quite a common technique used. Okay. Okay. Yeah, so the first remark is we can do something if we have less than L2 norm. And yes, the second remark is this is my paper. It's a slightly modification of the argument. What is maybe specific to the problem I address is that I need also to change the Schmidt decomposition, because in my non-divergence estimate I will talk about, I cannot have this for every dyadic interval of the form AB. I don't have the good non-divergence estimate for every kind of this dyadic. I need to restrict to some dyadic intervals, and so I have to sort out some sets from this decomposition. Yes, and the second remark is to say that what does it mean to have an L2 bound on these averages? I actually, if you multiply out, these averages, what we have is, this is actually double correlation. So this is simply sum over T1, T2 in some range of double correlations. So if I have a bound, actually, if I have an exponential equidistribution for these double correlations, then I will have the desired bound for my L2 norm. So what would give me this is a double effective, or yes, let's say some effective double equidistribution. Actually, it needs to be exponential. I mean, exponential would do the job. But of course, for this, it requires smooth, compactly supported test functions. So this will be a part of the approach, the refined approach. So. Require F in smooth, compactly supported. Okay, so yes, now maybe yes. So this effective double equidistribution so here I adapt. I think there are many genealogy of these results. So I take maybe the most general one I can use in my context. So I will quote, will make reference to a result by Björklund and Gorodnik, 21. Yes, and where they have this effective double equidistribution for unipotent orbits. And yes, and I claim that this works also for K orbits. So if I take test functions phi and phi and psi, smooth, compactly supported, and the density also smooth density on K. These double equidistributions, so they equidistribute to the product of the averages. Plus an exponential I mean, with the exponential error rate, delta minimum of these. So these correlations have to drift away one from the other. We have this rate, and the constants. These are some CL norms of the density and the test functions. I think these kind of results are familiar to you. So yes, there exists positive exponent such that for every full density function and for every test functions, compactly supported, smooth compactly supported test function on the base of lattices. Yes, and for every lambda in a compact, we have this exponential equidistribution. And the idea is to approximate, to use a partition of unity argument and to approximate locally k orbit, u orbit, k orbit by u orbit, and yes, and to find some, to use the result for u orbit to derive the same for k orbits. Okay, this exponential equidistribution requires the test function to be smooth, compactly supported, which is not the case for the Siegel transform. The Siegel transform is typically not bounded. So I need to approximate the Siegel transform by compactly supported smooth functions. So this is maybe the last. I approximate the Siegel transform by compactly supported, smooth compactly supported function in the space of lattices. And this approach is I took the inspiration from a work by Björklund and Rodnik. And they studied CLT for Diophantine approximants. So they yes. So the first step is to approximate. We approximate the characteristic function by a smooth function, smooth compactly supported function on the light cone. So we just take an epsilon neighborhood of the support of the characteristic function of our set of interest, and it's smooth enough, and we control. Yes, we have good control of this function in average. So in average, and also yes, the slope of this smooth approximation, the CL norm is epsilon to a negative power to minus L. But more important is to control this approximation on these translated k orbits. So this is what is more specific in this case. Yes, so I claim that the Siegel transform, that this approximation is also good, remains under control. If I take the Siegel transform and I average along these translated k orbits. So this remains under control. For every t, large enough. Yes, unfortunately, just L1. And that's one of the technical limitations. Yes, because how we show this, it's really a geometric argument. We look at the thickness of this epsilon neighborhood of this approximation, and we see that in the direction of this expanding flow, it remains. I mean, in the direction of the expanding flow, this epsilon neighborhood has the good width. So it's never parallel to this neighborhood. Yes, and this argument, I couldn't do it for the L2, for the double, for the L2 norm. And maybe you will see soon why this L2. I mean, the L2 norm of the Siegel transform is problematic here and also in the next approximation. Yes, and the second step is to approximate the Siegel transform. Well, the Siegel transform of this new, the Siegel transform of the smooth approximation. This is smooth but not compactly supported. So we approximate this by a smooth compactly supported function. We just truncate. So this is smooth compactly supported. This is a truncated Siegel transform. And we truncate it. This truncation is constructed in the following way. We just multiply by a cutoff function, eta with parameter L, and eta L is the convolution of some bump function with the characteristic function of the set where alpha, this alpha function, the alpha function which measures how far in the cusp the lattice is less than L. So in X, so we just cut off L here. We cut off all the lattices that are beyond this border. Yes, and for this truncated Siegel transform, we have also good estimates, so it's bounded. Well, more generally, for a truncated Siegel transform, this is bounded. Depends on parameter L. L will be taken to go to infinity, large to grow. And also the same for the CL norm. CL norm is also controlled in terms of parameter L. And again, more important is to control this approximation on these translated K orbits. So the Siegel transform on, and so the error, the approximation to the truncation of it on average on this translated K orbit is controlled. And here I really need to have better than L1. I cannot have L2 for the same reason. I cannot handle, I mean, I have problems with L2 norm of Siegel transform, but at least for some P smaller than 2. So I have a control of this as a negative power of the parameter L. And again, this holds for large enough T. Yes, and this estimate is, I think, is a little bit more interesting. I mean, I found it interesting to study. What we use here is, yes, we first, yes, I need maybe to say something, but I guess you know what this alpha function is. This is the inverse of the shortest vector in the lattice. What I want to say is yes, maybe just that this alpha function controls the growth of the Siegel transform. And we have a nice non-divergence estimate for this alpha. I think you can also call it non-escape of mass. Non-divergence of this alpha function, which controls. Oh, yeah, maybe I have to say something also very important here. Is I don't have an L2 bound for the Siegel transform, so I used the best thing known to me, which is an old result by Eskin, Margulis, and Moses from 98, which says that the average of this alpha function on the for every P strictly smaller than 2 is finite uniformly in T. The supremum over T of these averages is finite. So this helps to make this boundary. And the non-divergence of alpha is just saying that the proportion of the K orbit, which is high in the cusp. So high in the cusp, the proportion here gets smaller and smaller when we push by AT. So this is smaller than L to some negative power. Some negative power of yes, for every power less than the dimension. Yes, and for every T large enough. Okay, so this when these K orbits pushed by AT, so the proportion here, guys, is controlled in terms of the parameter L. Voilà. I think yes, and now when I have this, I have. No, for unipotent orbits, this was in the work of Björklund and Gorodnik. So I adapted the argument here for this specific for K or orbits in this specific space of lattices. Yeah, so I have actually everything now to wrap all these estimates and have the I have the estimates here I want. So for the smooth compactly supported approximation, I have effective exponential equidistribution, which gives me L2 bound, which gives me the pointwise effective equidistribution. And for the errors coming from the approximation, I have these non-divergence estimates that help me have the good. And then playing with this parameter. So L is a parameter function of t of n, epsilon also, and playing also with the p of the LP norm, we managed to have this power saving for the counting function. I think that's all what I wanted to say. Thank you.
Any questions?
Can you give us an idea of how you go from unipotent orbits to K when you prove this, essentially reprove this Bjorklund-Gorodnik result?
Oh, for K?
Yeah.
So locally, so I use a partition of unity to local, actually in the neighborhood of the identity. Then I decompose K. I decompose K as a product of an element in U minus in H. H is subgroup which commutes with the group with elements in the group A, and U minus an H. And then so I can take out the elements in H which commutes with A and have no effect on the dynamics. And what remains, I also decompose it. I use that this decomposition is a diffeomorphism, so I can really control when I do a change of variables between K and U, and I show that this change of variables is a diffeomorphism, so I can control the averages and the density of this change of variables is also uniformly bounded. So it gives the equidistribution the same exponential rate.
It's a question about the literature on intrinsic approximation. So is there a Schmidt theorem? You mentioned Schmidt, but you only used a special case of Schmidt with where the growth is linear, but Schmidt has a general Khinchin theorem with an error term. So the question is there a Schmidt-Khinchin theorem with an error term in the spirit of Schmidt for intrinsic approximations? Has somebody done that?
Not
No?
that I know. No.
Anish says no.
Not that I know. I think your result was the first quantitative result for a variety. Yes. With the Dirichlet approximate, with this critical exponent.
It's an interesting open problem for those who are looking for interesting open problems.
So I think your approach also shows that you won't expect an asymptotic for alpha that are in the residual set, except if they correspond to an invariant measure, say, to some periodic orbit or something like that. Right? Have you looked at that?
No.
Because you have the Birkhoff-Ergodic theorem also for other alpha. Maybe your variance estimates and so on don't hold, but probably one could show that there are certain alpha for which you don't get convergence, for which you don't have a main term in your asymptotics.
I haven't looked at the.
Any more questions? If not, let's thank the speaker again.